Okay, so this is going to be an introductory talk on multilinear algebra. Uh, the book we'll be reading, Spin Geometry, starting November 22nd, does cover some geometric algebra concepts in the first chapter, but it does presuppose familiarity with such things such as tensor products and exterior algebras. So that's what I'll talk about. Uh, in order for this talk not to go on forever, I have to suppose some familiarity with basic linear algebra. So I'll assume that you know what a vector space is. I don't think, I mean, well, I'll assume you know what a vector space is, what linear maps are. Just some things you see in your first semester. And at some point, I'll assume you know some stuff about permutations. So I think that's everything I have to say beforehand. We can get started. And the starting point of multilinear algebra one can take is the concept of multilinear maps as opposed to linear maps in linear algebra. And so first, let's fix some stuff we'll need throughout, kind of ambient data. So we'll suppose that K is a field, and I wrote commutative, that's what the book does. It used to be historically that many people didn't uh, require fields to be commutative, and they just considered what's now called division rings. But we'll do the theory over commutative fields since it's a bit nicer to work with. And a lot of these things you can do over arbitrary commutative rings, and then the vector spaces you get what's called modules. But for the purposes of this book, um, even though there are modules over Clifford algebras, I think, this is essentially the relevant situation for us. So let's fix a field, uh, and let's fix some notation for vector spaces of the field. So the definition that we'll be looking at throughout this talk is the following. We take some vector spaces and take the product space and a map out of that. And so our vector space is called multilinear or n-linear, where n is the amount of the vector spaces. If whenever we fix all but one of the components in the map, we get a linear map. So a very simple example of this is multiplication or scaling. So of course, any vector space we can scale the vectors by scalars. And this is a bilinear map if we regard the field as a vector space of itself, dimension 1. Then we've got this mapping which just takes a scalar, takes a vector, and it scales the vector by the scalar as the output. Now it's bilinear because if we fix the vector, we just get a map of the form lambda maps to some multiple of a vector. And vice versa, if you fix the scalar, we just get some scaling for vectors the map. So some things to immediately note. If we take a multilinear map and first do the multilinear map, then do a linear map, then all of the conditions on the component fixed maps to be linear translate to the composition for those component fixed maps to be linear. So we get this property. Now, as a corollary of that, if we take two multilinear maps and take the direct sum, assume they have the same the domain of definition and same codomain. So there are a few typos here. This should be the product of V1 through Vn, and the previous slide this should be K, not R. Then we get this map, which takes some array of vectors and maps it to the formal sum of the first map evaluated them, the second map evaluated them. And we get this new vector space, and on that vector space we have a linear map which just takes some formal sum a plus b and maps it to just the usual sum in the vector space, in this case u, a plus b, or here uv. And if we compose, we see that if we take two multilinear maps with the same codomain and the same domain, then the sum is also multilinear. Now, as a corollary of these two remarks, we see immediately that if we take the space of all multilinear maps on some given domain, some fixed codomain, and then we get actually a vector space. And so this kind of reduces some parts of multilinear algebra to usual linear algebra, and kind of the setting one can try to devise to study multilinear maps in general becomes that of so-called tensors. And so, well, this is not quite a formal thing that I'm writing here, talking about, but essentially, intuitively, we wish to kind of capture this notion of multilinearity in some sort of object that we can work with multilinearly. And so in linear algebra, we do this with vectors, which we can work with linearly. In multilinear algebra, we wish to work with something with kind of multiple factors that are put kind of in a product wise, since that's the prototypical example of multilinearity is with the scaling example, kind of product wisely put together into one thing. And that's the concept of a tensor. And so kind of morally, what we wish is to have some sort of idea of a multilinear map, which takes a bunch of vectors and kind of gives them a combined multilinearly joined tensor. Now, of course, this is rather vague, but this is how we wish to approach, or how it's common to approach the formal study of multilinearity. This has its advantages because once we have done this, we can, instead of thinking about multilinear maps as maps, instead think of these sort of multilinear objects. And I also note that with something like vectors, a vector space is a structure that doesn't require kind of external structures to function, except perhaps the field, you could argue. But with multilinearity, any multilinear map has multiple factors, or it could be 1 or 0, but some amount of factors in its domain. And so we wish tensors to be kind of made out of parts, made out of vectors. In fact, tensors themselves should intuitively be vectors, because if we wish to consider this multilinear map and kind of intuitively all the multilinear things you can do with it, we've seen that all the multilinear maps are, they form a vector space. And so intuitively, the space of all tensors should also be a vector space. And so we can just kind of formally construct what we want, the sort of free construction of a multilinear map, which also has a formal meaning, but I will not go into too much. So we can define a tensor to be a certain kind of multilinear expression, so to say. And so what I mean by that is we take some vector spaces, we'll take as our factors to make the tensor out of. We take the free vector space, which has as its basis elements of the product space. So you have to be kind of careful. We have the, for example, let's consider the vector space R2. So R times R. Let's do it as such. Then if we take the free vector space about that, which I've noted here with this mathrm free expression, then you would have the vectors 1, 1 and 2, 1. And those would be, oh, so let's say 1, 1 and 2, 2. Those two vectors, and they would be linearly independent as elements of the freely constructed vector space, because substantially just kind of putting them there as formal expressions, we're not imposing the vector space structures they arise from on the free construction. We're just viewing them as elements of a set. And so in this slide, the notation I use is that given some vectors vi in capital Vi, then this expression m of v1 through vn, it's the kind of formal jointness of these vectors, formal, the element of the free vector space generated from this product. And now if we wish this construction, so we've obtained a free construction, which is kind of, we generally put them together, but we want to have a multilinear construction, kind of put them together multilinearly. So in some sense, we wish to make this map, which takes these vectors and puts them together formally in a completely independent of each other way. We want to make this map multilinear in some way. And so all we have to do is just impose this multilinearity, which we can do by taking the expressions which we want to identify for the map to be multilinear, and quotienting by the corresponding differences. Because given it's a vector space, if we quotient by a subspace, we will identify everything in that subspace with 0. So if we choose such expressions whose identification will make the composite map of first this formal joining of the vectors and then the projection of the quotient, the multilinear, we'll get exactly what we wish, a sort of free multilinear construction. So uh, linearity consists of two conditions. First, homogeneity, that if we scale a vector and then map it by a linear map, then the value we'll obtain will be the corresponding scaling of the value of the linear map at the vector. And so we get this first expression we desire to be identified with 0, namely that if I scale the formal joining of v1 through vn by some lambda, this is the same thing as if we imagine that all but vj for some j are fixed in the formal expression and the j scaled by lambda. And so we take the difference of these two and this must be 0. And so we can put that in our subspace and then do the same for sums, which is just completely analogously. We fix everything but some jth component in our freely constructed vector in the free vector space, and identify that the sum, if we take this and replace the jth component with the sum of two vectors in Vj, capital Vj, then that will be the same as if we replace it with one of these vectors, one of the summons, and the other in sum we have. So if we generate this linear subspace by all these expressions, by all these vectors in our free vector space, and take the quotient, we'll have this sort of way of joining vectors multilinearly, exactly what we desire. And so that's the definition of a tensor product of some finite number of vector spaces over the same field. We take these vector spaces, v1 through vn, we form the free vector space on the product, just viewing the product as a set, and quotient by all these relations that ensure that if we first take a n-tuple of vectors, interpret it into free construction, and then go to the quotient, identify all the things we need, we'll get a multilinear map. And so some common notation is that we'll write for this tensor product v1, and then instead of doing a multiplication cross, we do a circle multiplication cross just to kind of differentiate. It's still a very multiplicative concept. I said the idea of multilinearity is very related to multiplication in a way we'll see near the end of the talk. And we just write this expression then for the tensor product that we have, that it is v1 kind of O times through O times vn. And then kind of abusively, we also use the symbol to the circled multiplication sign to denote the resulting vectors in the quotient, the sort of tensors. So tensors are then the elements of this vector space we obtain, these sort of free multilinear combinations. So if we have some vectors v1 or in v1 and etc. through vn in vn, we can view them as an n-tuple in the product of these vector spaces, then view that inside as one of the basis elements in the free construction, free vector space construction on this product, and then identify the things we desire, and then we obtain this tensor, which we also denote the same way as if those were vector spaces with this circled cross. Now, one important thing to remark is that these are only what are known as pure tensors, and they're also, we can take sums of these. For example, I could take in, let's say, R2 tensor R2, E1 tensor E1, where EI is the I standard base vector, and add to that E2 tensor E2. And there's no way to write that as a expression just as a pure tensor product, as a pure tensor. This comes from the fact that when we do the free construction, the product of vector spaces, elements, they are not just n-tuples of vectors. They are linear combinations, those formal linear combinations that we are setting this as a basis, those n-tuples. So we can actually note that this construction kind of very, well, we can note that this construction appropriately captures the notion of multilinearity. Namely, any multilinear map out of our product of vector spaces is going to factor through their tensor product. And alternatively, any multilinear map or any space, any vector space with the same property that any multilinear map out of the product into some vector space factors through this vector space will be the tensor product. So exactly what this means is the following. suppose we have some vector spaces we run through Vn, and suppose we have some multilinear map out of it. So M from V1 times etc. times Vn to V. Now, if we have any, so suppose we have the following condition. If you're giving a multilinear map out of this product into some U, then there exists a unique linear map from this V to U such that we can, instead of going by the multilinear map directly to U, first go to our V and then apply this uniquely existent linear map. Suppose we have this condition, then it can be quite directly shown there's an isomorphism, a unique isomorphism from V to the tensor product V1 through Vn, such that if we look at what this map M corresponds to on the isomorphism, we get exactly the canonical map we have from the product tensor product, first doing the free construction and then going to the quotient. And so, of course, conversely, I didn't write this down on the slide, but the tensor product itself, if as V, we take V1 tensor tensor Vn, and as M, the canonical map we get by first going to the free construction and then taking the quotient, the tensor product will have this property. So, kind of in a category theoretical sense, this means that the tensor product of some finite family of vector spaces, so the same base field, is the initial multilinear map out of our product of those vector spaces. So any multilinear map factors through it in the sense that there's a linear map between the codomains, a unique one, such that the composition equates. So in this sense, we kind of can note that our construction truly works to capture the notion of multilinearity. So it's a useful thing to look at. Whenever you have a multilinear map out of some spaces, this corresponds exactly to a linear map out of the tensor product. And this characterizes the tensor product uniquely. So perhaps more concretely, the reason we chose as our scale as a field in this talk and in the book as well is that whenever we have free vector space, so free modules in this case, so the theory of general modules over commutative rings, so abstracting away and allowing, instead of say taking complex vector spaces, taking so to say vector space over the integers, whatever that means, there is the possibility that one obtains vector space, so in this case they are called modules, which do not possess a basis, like the standard case over a field. And when they do possess a basis, they're called free, and so over a field, all vector spaces are free. And this is rather quite convenient because we can quite directly, through definition, show that if we have bases for some vector spaces Vn through Vn, then if we take all the possible tuples of elements of the basis and look at them interpreted as tensors of pure tensors, so as they take the tuple and then we, instead of the commas, put the tensor product sign, that will be a base of the tensor product. Now, that's not a completely trivial claim, but it follows directly by computation. You can just verify that given the linear independence in the factors, if we have some linear combination in the tensor product that equals 0, you can verify, we can pull it back to the free construction and note that then this expression has to lie in this subspace, and then that all of the coefficients must be 0. And the fact that this spans the tensor product one sees quite immediately, because by definition, the free vector space on some product is spanned by elements of this product, so by just n tuples. And once you go to the quotient, of course, an image of a spanning set is still a spanning set. So because of that, we get that the span of the image of these bases, of the product of these bases, is indeed the whole tensor product. So this is quite convenient to get a sort of grasp on how these things behave. We can, because of that note, well, the cardinality of a product of bases is just the product of the cardinalities. And so if we consider the dimension of the tensor product, it will be the size of the basis of any basis. And as you've seen, it will be the product of the sizes of the bases of the factors. So this kind of has it that if we want to take the dimension of a tensor product, we just multiply the dimensions of the factors. And so this also explains one way tensors are commonly considered. So if you ask, say, a computer scientist or programmer what a tensor is, a very plausible answer you might get is the fact that a tensor is an high dimensional array or arbitrary dimensional matrix. And so what this can be took to mean, well, in the case of vectors, what this means is a vector can be always written as a linear combination of some basis elements. And then the coefficients can be just put in the array, and we can think of the vector as these coefficients in the arrays, this array of scalars. Of course, given we have some immediately chosen basis, which in practice is always just a standard basis, and one works with powers of the field. Now, in this case, we have that given a tensor product of some vector spaces, it's essentially has as elements linear combinations of sort of n tuples of base elements of those corresponding vector spaces. So not really n tuples, rather pure tensors made out of these base elements. And so you can think of, say, in the case of two vector spaces, v1 and v2, if you take their tensor product, then any element there will be a linear combination of expressions of the form AI tensor bj, where AI and bj's are basis elements of respectively the first vector space and the second vector space. And so we get these two dimensions of coefficients. In three dimensions, have three dimensions of coefficients, etc. In three dimensions, I mean, with three factors. I mean, this is exactly what's written here, where we have this sort of product in the exponent of our field. Notationally, you can interpret this as the space of all kind of d1 by etc. by dn matrices, or well, high dimensional matrices, meaning you have n indices, the ith ranging from 1 to di. And so this is one way you can think of tensors. Now, something to note, another way to think of tensors, we can just very concretely look at what pure tensors look like and try to visualize those. So it's not difficult to verify specifically because we have this basis dependent description that two pure tensors in some ambient tensor product equate exactly when we can kind of pull out factors out of each of the factors in the tensor product such they all equal to 1. So for example, if I took 1 tensor 2 and 2 tensor 1 in the tensor product of R with itself, then I can kind of pull out the 2 out of the second component, put it to the first, and then I see that those are the same, because then we'll have 2 times 1. 1 is 1, 2. Yes. In general, this yes can be seen to be true in any tensor product vector spaces if we just write out each of these vectors in a basis and then use the multilinearity of the map. So also in the, if you're wondering how I did the computation with pulling out the 2 of 1 tensor 2 equals 2 tensor 1, that's specifically just the fact that this map is multilinear. But so the useful thing about this is that we can kind of try to visualize things geometrically. Now, usual vectors you can think of as sort of arrows in, well, let's take as our base field the reals for purposes of visualization. You can think of as a vector in RD as a sort of d-dimensional arrow out of the origin. Now with tensors, you can do something similar, except now we don't have one arrow. We have multiple arrows because they're the factors of the tensor product. And those arrows, they're not unique because we can scale them and the scaling moves over. So for example, so let's say I want to visualize the tensor 2e1, tensor e2 in R2 tensor R2. I can just kind of draw the arrows and think of the parallelogram, or in high dimensions, high dimensional version of a parallelogram, they span, and think of that as the tensor. Except now one has to consider the fact that I can squish this parallelogram in one dimension and instead have it scale in the other, long as the area remains the same. It will be the same tensor. And another thing one has to consider is that tensor products are not symmetric, whatever that would mean. I mean, first of all, you can take a tensor product of, say, something like the reals with the complex numbers, both viewed as rational vector spaces, or we'll say real vector spaces. And then the elements of the first and the second factor are kind of fundamentally different in nature. You can have different vector spaces you can tensor with each other, take a tensor product of. And so, in general, it does not even make sense to say that A tensor B equals B tensor A for pure tensors. If your base space is the same, it means your base vector space that you make vectors, make tensors out of. So, for example, if you take R2 and tensor it itself, then of course it makes sense to say that A tensor B equals B tensor A, but fundamentally there's no reason why that should be. Multilinear maps do not need to have this symmetricity property, which is specifically something you can require them to have. And so when we visualize tensors in this way, pure tensors in this way, we have to keep in mind that we need to label each of the arrows in the order they appear in the tensor product. So in particular, if I do E1 tensor 2E2, this is not the same thing as doing 2E2 tensor E1. So this is what the numbers I wrote in refer to. They're not lengths or sizes, they are the ordering of which vector comes first, which comes second. So in 2 dimensions, or with 2 factors, we have 2 options. With 3 factors, we have 6, because that's the number of ways to order 3 vectors. In general, with d factors, we'll have d factorial options, which is quite a large amount. So there's really a lot of redundant information here. But this is one way you can nonetheless visualize pure tensors. You have to be careful. Of course, not all tensors are pure. I can do something like E1 tensor E2 plus E2 tensor E1. And this no longer can be written as just a tensor product A tensor B, and so you cannot draw it this way. You have to really kind of decompose it into pure factors and then think of it as the sum. Another thing you have to be careful of, you can have a tensor like E1 tensor E1. There's no reason why this should be 0. In fact, you can prove this is not 0. And so you get kind of this multiplicity going on. So that's something that you have to consider. Okay, so another important thing to note about tensors is that we can kind of multiply them together. I mean, it makes a lot of sense because, well, it's called a tensor product, and notation is that of products, except with circles everywhere. But I can just kind of formally, if I take some tensor v1 tensor etc. tensor vn, and some completely unrelated tensor u1 tensor etc. I should say ul. That's my bad. Doesn't have to be the same length. Then we can define a new tensor. We're just kind of doing this construction inside of the tensor product of the factors of the corresponding tensors together jointly. This seems very kind of algebraically nonsensical, just a bunch of simple manipulations going on. This is not a trivial thing to note. You have to verify that this makes sense, because remember, a tensor, even if it's pure, is not uniquely given by these factors it's made out of. Again, 2 tensor 1 is the same thing as 1 tensor 2. And in general, a tensor doesn't even need to be pure. You can have multiple summons. And so the fact that this suffices to uniquely determine a map follows from the fact that pure tensors span the whole space of tensors. And the fact that this is well defined has to be verified. You can do this with the universal property of the tensor product. This fact that it's the initial multilinear map. So then you can just reduce it to looking at linear maps. But either way, you can verify the details for yourself. Actually, I think if you're not sure what's going on, I highly advise you try to verify the details again. Remember, sorry, there's a typo here. The UN should be a UL in the second equation, or the second map. Verify that this makes sense. There exists a unique isomorphism given, or that maps expressions as v1 tensor etc. vn, that tensor u1 tensor etc. un to just them all tensors together. I think that makes this confusing is the fact that we're really heavily abusing notation here. The tensor product here means 2 different things. One is the tensor product of spaces, and the second is the tensor product of like the elements in the spaces when we put them together. So the multilinear map corresponding to the tensor product. And so maybe I should have color coded them here, but just one thing, do them on elements and another on spaces, and as well you can do it inside of different tensor product spaces, which makes it confusing as well. So really, if you look at the second row, the left-hand side, we have three kind of tensor product signs. We have on the left the tensor product sign corresponding to putting V1 through Vn into the tensor product of capital V1 through capital Vn. Then the second kind of tensor product, the one between Vn and U1, is the one of putting the left tensor and the right tensor together into the tensor product of the tensor spaces. And then the third one has with V1 through Vn just with U1 through will. So in particular, because we have a map which, given an n tuple of vectors, interprets it as a pure tensor just by tensoring them together, this canonical multilinear map, this gives us a way of bilinearly kind of multiplying tensors together, even if they're in different spaces. So we kind of have this notion of multiplication, which is quite convenient. So again, the construction that one does is one takes two tensors and then just kind of puts them next to each other and tensors them together. And you can verify this makes sense via kind of verifying these claims here. So we can also try to visualize this. Let's consider taking the tensor product, or this kind of external tensor product, just a tensor product of different tensors of the tensors in R2 tensor R2 and in just R1. So let's take some tensor in R2 tensor R2, for example, E2 tensor 1, 1. I've drawn it on the left here. Actually, perhaps I've labeled the yeah, sorry, this should be, what I've drawn is 1, 1 tensor 2. Yeah, I apologize for the typos. So I should be numbered the way around. So that doesn't really matter. I guess you could say you just read it the right way. So you take one tensor and take another one, and in order to kind of multilinearly put them together, when you visualize them as these n-dimensional, arbitrary dimensional parallelograms, you can just kind of stick them to each other. You're taking the Cartesian product. You can formally define these parallelograms as subsets and then take the Cartesian product and get another parallelogram. Of course, you have to consider equivalence classes of these parallelograms because they can scale, but you kind of have this visual for them together. It's a little bit different from what we were doing earlier because this is now combining dimensions, so to say, but this is what we get. And in the picture, it's something to notice that we are tensor producting with a one-dimensional vector space, just with the ground field. And so any sort of scaling that goes on in the scalar component can be took out of the scalar component into other ones. You can imagine if the red arrow, the red tensor, were twice as large, just scaled by 2, then you can just scale that down by 2 and take this factor of 2 into the other dimensions. So essentially, this dimension we've added doesn't change anything. And so in fact, you can observe that if we take a vector space and tensor it with the scalar field, we'll just get the vector space back. So formally, again, if you think of an expression on the left-hand side, this is going to be a tensor of the form, a sum of pure tensors of the form V tensor lambda, where V is some vector in V and lambda an element of K. Then you can think that V tensor lambda is the same thing as lambda times V tensor 1, where times means scaling into tensor product. And then I can just take it to the left side, because this whole bilinearity of the tensor product map works, and we get that this is the same thing as lambda V tensor 1. So in fact, any element of the left-hand side here is a linear combination of pure tensors of the form V tensor 1, and so it's just basically, you can get, it's something of the form some vector tensor 1. And this vector you can just take as an vector in V, and we get an isomorphism. It doesn't really change anything. You can take the scaling to other dimensions. This also makes sense with the dimension formula we saw on the previous slide, or 2 slides ago, because K is one-dimensional. So if you take the tensor product of it, you're multiplying the dimension by 1, doesn't change anything. So there's no way to see this. Okay, but so turning to the sort of product notion, we get a notion of what's called an algebra. And there are very many possible definitions of what an algebra is, useful in various branches. The one that we want to use here is that it's any vector space together with a bilinear map mapping vectors from the vector space back to itself. Often one will also want to require other conditions in the algebra, such as, for example, this map be commutative as a binary operation or have a neutral element. There are many options. We just require bilinearity. This is sort of the almost most general notion of an algebra. The only way you could generalize this is by, this common, is by allowing ground commutative rings for scalars instead of fields, or just round rings. And so that's an algebra, just any vector space with a bilinear binary operation on it. And using this definition, we can interpret tensors made from some vectors in some fixed vector space as an algebra. This is called the tensor algebra of a vector space.
Are we assuming associativity?
Okay, yes, a question from the audience. It's not on the recording, so I'm repeating. No, we're not. So the question is, do we assume that algebras are associative? And no, we do not need to assume that they are associative. I mean, again, you could assume, you could put as many conditions on your algebras as you wish. But really, for the purposes of what we're doing, all the constructions work perfectly well with non-associative algebras. I mean, really, in this talk, we'll mostly just look at examples of algebras. So we do not need to assume that they're associative. And actually, there are many useful examples of algebras that are not associative. We'll come to see, I think, in the geometric algebra book, in the spin geometry book. No, we do not assume that. This is pretty standard in commutative algebra to, when considering algebras in the context of modules, not to assume that they are associative. So if you also look into, say, Eisenbart, I'm pretty sure he doesn't assume that they are associative in the appendix. But so yes, we can form the tensor algebra of any vector space just by considering all the possible tensors you can make out of vectors of this vector space. So you just take the tensors which are made from two vectors in the vector space, or three vectors, so A tensor B tensor C, or the combination of those. Also from one vector. Any vector is trivially a tensor just in the tensor product of the space with nothing else, just kind of this singular vector space tensor product. And I mean, you can think of it, any linear map is one multilinear, so just one linear. So because of that, vectors are also tensors. And also you can take the tensor product of zero spaces, and you can also think about that. The zeroth power of any vector space is just the scalars. You can kind of argue what that should be if you think about how dimension should behave. So kind of zeroth order or zeroth degree tensors are just scalars. So really, if this direct sum looks a bit confusing, you can think of it as the scalars direct sum the vectors direct sum like non-trivial tensors. So elements of v tensor v, and then v tensor v tensor v, etc. Oh, again, another typo. This should say, I mean, I use one notation above, one below. I've tried sticking to the notation the book uses somewhat. I mean, there are many different ways of denoting things. So the book uses tensor to the power iv. Some people write v to tensor I. But yes, that's just repeated tensor multiplication of the vector space itself. And so this is the vector space they have, because we can take direct sums of vector spaces. These are all vector spaces we've seen tensor products of vector spaces. But we also need a bilinear map on this binary operation to make it an algebra. And for that, we can use the map we've seen above. We just take two elements of this direct sum. And of course, they will be linear combinations of elements of these repeated tensor products of the vector space itself. But what concerns bilinearity suffices to just consider a generating set, some spanning set. So we can just consider elements in the ith tensor product of v with itself and the jth. And there we have those, again, spanned by pure tensors. We can just consider pure tensors of kind of degree or order, rank I. I mean, there are different ways of calling it. And rank j and then we just put them together as in the construction above. And so in this way, we have this sort of tensor algebra we can work with. It's quite a convenient thing to work with. It also has a universal property similarly to the tensor product of vector spaces, but then for maps of algebras. But I will not go into that. That's not something we will require in the book. And I mean, it's pretty analogous. It can be derived from the tensor product universal property. So it's a pretty important construction. It can be used to construct many other algebras. In a sense, this is the free algebra on a vector space. I will not go into what that means, but there are many sort of freeness in general means the imposition of no unnecessary conditions. And so in a way, if we just want a bilinear map, we can just only do things that we need for multilinearity, put them all together, and kind of generate this algebra. That's essentially the universal property of the tensor algebra. But because of that, we can generate many other examples of algebras using this, specifically as quotients of this algebra, of the tensor algebra vector space. So in general, as I assume the audience of this talk will know, you can take any vector space and quotient by a subspace I've already used this in previous slides, in constructing tensor product, say. However, if the vector space we start with is an algebra, then in general, the quotient will not be an algebra. So an example of this would be if you take the complex numbers and the multiplication. This is a real vector space. You can just scale as you would. And if you then take the real subspace of the diagonal, all the complex numbers with the real and imaginary parts equate. If you go to the quotient, it's not really going to work any nicely to define the multiplication on. And the problem here is the fact that, well, if you quotient by a subspace, you identify it with 0. And so when you want to induce the product onto this quotient, you need that multiplying anything by anything in the subspace will remain in the subspace, because anything times 0 has to be 0. This in general fails. In my example of the complex numbers at the diagonal, if you take 1 plus I and I, something in the subspace and something outside, so in the quotient something that's 0, something that's non-zero, you multiply, you get I minus 1, something outside the subspace, so in the quotient something that's not 0. That cannot work in a algebra. Why? Because any multilinear map maps some tuple of vectors of which one is 0 to 0. You can simply write 0 or 0 times some vector and pull the 0 out by multilinearity, fixing all the other components. So because of that, we need to require this condition on subspaces, and the resulting notion gets the status of ideals. An ideal is any linear subspace such that when you multiply something outside the subspace, or just not something necessarily only outside, just anything by anything in the vector space by an element of the subspace, we remain the subspace. Then in the quotient, this means precisely that if you multiply something that's not 0 or just anything by 0, you get 0. Which is something that we need for linearity. And in fact, it suffices to see, this is something you can note that it suffices to induce a bilinear multiplication. So to see that it's, to see that it's well defined, follows exactly from this condition. We can just kind of translate everything to 0. So let's, if you look at the very bottom of the page, let's suppose we want to verify that on the quotient we get a well-defined multiplication by just multiplying representatives and making the equivalence class. We take some equivalence classes A and B, equivalent classes of representatives of A and B. Ideally, we wish to define their product as the equivalent class of AB. Now, for this to be well defined, we need to suppose that if A and A prime are equivalent, and B and B prime are equivalent under our equivalence relation induced from I, so the differences lie in I, they are 0 in the quotient, then the product AB will be equivalent to the product A prime B prime, so the difference will be in I. And this is just a direct computation. If we suppose that A minus A prime and B minus B prime is in I, then AB minus A prime B prime is A minus A prime plus B minus B prime plus AB prime plus A prime B, just by bilinearity of multiplication. So bilinearity translates to distributivity plus scaling working. And we know that the first factor is in I as a product of two things in I, and then the second as something arbitrary. No, 1 second. AB prime. Okay, I might have a mistake here, I have to think. So AB, A prime, B prime. I mean, the condition does suffice my justification. I mean, AB minus A prime, B prime has to be in I. If we factor this like this and then add this should work. Okay, I must admit, I'm not quite sure what's going on here. AB prime. Okay, perhaps we can talk about this after the talk and verify again. I'm sorry about this. But the condition is correct. I mean, it's very common that you want to take quotient like that. But yeah, I guess maybe I made some reasoning. I didn't use the correct reasoning here. But anyway, if you have something where the 0 multiplication works, you can check that indeed AB minus A prime B prime will be in I whenever A minus A prime and B minus B prime are. Yeah, okay. Well, we can come back to this after the talk. So this way we get a quotient algebra. And using this, we can construct a lot of examples of algebras, except before that, it's also convenient to note a different thing, namely that given any subset of an algebra, we can take the smallest ideal containing the subset. we can note that the intersection of any ideals is an ideal just by verifying that, well, for subspaces this is true. Well, in general, this is a very uh, common phenomenon that you have some sort of conditions you give, and they are preserved under sort of conjunction, on the intersection of the things that satisfy them. And you can define this in a very general context. And so this also works for subspaces and for ideals. So the intersection of any ideals is an ideal. And then whenever this is true, you can take the smallest ideal in this case, containing something just by intersecting everything, all the ideals that contain it. And noting that, for example, the whole space is an ideal, and so there is some ideals to intersect. There are. So what this gives us is that given any subset of an algebra, there's a smallest ideal containing it, and that's the ideal generated by it. And so if we want to obtain some algebra of some form, we can give a sort of presentation of it by saying we take the most general algebra we can think of, the tensor algebra from vector space, and then we identify some things by generating an ideal thinking quotient. So a common example is the exterior algebra of vector space. So we start with the tensor algebra, and then we quotient out all the sort of squares, all the elements of the form V tensor V of the tensor algebra. Of course, we have to generate the ideal. What we obtain then is called the exterior algebra, and expressions there are, or elements there are of the form equivalence class of a tensor product of some vectors in V, or some of these. And the notation one uses is one denotes the whole algebra by capital lambda V, and elements by replacing, upon taking the equivalence class, the circle product with wedges. And then one calls these expressions, these elements V1 wedge, etc. wedge VR, the R blades of the vector space. Now, in the tensor algebra, we have these various orders or degrees of tensors, and we have the elements of the corresponding tensor powers of the vector space. If we take the image of these tensor powers under the projection from our space into the quotient, we get what we define as the exterior powers of our vector space. Since an image of a linear subspace is a linear subspace, we know that these are vector spaces. And we can note that indeed, because things work out with direct sums, the exterior algebra conversion is a direct sum of these exterior powers of a vector space. So this kind of gives us a separate notion to investigate, kind of an analogy with tensor algebras. And in fact, there are many other algebras you can construct this way, and we will see some in the book. We'll see the Clifford algebras, which are a whole family. We can construct a symmetric algebra, which instead of quotienting by things generated from V tensor V, you quotient by V tensor W minus W tensor V, so no longer pure tensors you generate from. And there's a lot of things you can do, but the one most relevant for us and in the book is the exterior algebra. It's also very useful in differential geometry, which we'll see in talks to come. And something to note about it. First of all, just by a quick computation, let's see if this one is right. If we take two vectors, u and v, and view their wedge in the second exterior power of the vector space, then one can note that if we actually take the sum and wedge that with itself, well, by definition that's zero, because that's at least the ideal. And then we note that this wedge has to be bilinear because it's a multiplication in our algebra. That follows from how we constructed quotient algebras. And so we can expand it out, kind of open parentheses. We get u wedge u plus v wedge u plus u wedge v plus v wedge v. U wedge u and v wedge v is zero by definition of how we construct the exterior algebra, and we left with v wedge u plus u wedge v. So if we return to just the wedge of u and v, we know that the sum of that and v wedge u is zero. So we can bring v wedge u on the other side, note that u wedge v is negative v wedge u. And this is kind of equivalent to the condition we started with, provided we have some light condition to field memory that's not characteristic to, we'll come to this later. So again, there's some abusive notation going on that we have to be a little bit careful of, especially if somebody's first seeing these concepts. Just like with the tensor product, this wedge here is used for two purposes. One as the multiplication on the exterior powers or the exterior algebra of a vector space, and one for kind of notating the elements, just completing an analogy with the tensor algebra. So using this observation, we can actually note that, well, in the tensor algebra and tensor powers, if you want a basis, we just start with the basis of the vector space, take all the possible tensor products of the elements. They can repeat, and they can be in different orders, and those all will be linearly independent. However, now if you take exterior powers, if you say take the second exterior power of R2, then we have something like E1 wedge E2, and that's the same as negative E2 wedge E1, so they're linearly dependent. So in fact, the only thing that matters is the set of the vectors that are contained in our oblate, or are wedged in our oblate, the kind of factors. And they cannot be the same because otherwise we get zero. And so what one can remark is that if we start with an ordered basis and we require that we take wedge products of strictly increasing base elements in our ordering, so we've just ordered like E1, E2, E3, then strictly increasing would mean E1 is less than E3. We take these wedge products, take these plates, then that will form a basis of our exterior, our R of exterior power, where R is the amount of vectors we wedged. The reason that this is corollary to the fact that we can do the construction with all the possible orderings for the tensor product. So we know that if we do all the possible bi tensor etc. bj of length r, I guess bi1 tensor etc. bir, this will be a basis for the half tensor product of v, and then we can just kind of simmer that down to only the ones we need for the exterior algebra by using the conditions we've seen. Then to see linear independence, you again have to kind of go into the ideal we used to generate the algebra, but you can verify this. Now, in particular, in some sense, basis elements are subsets of the size, which corresponds to the power we take of the vector space using the exterior construction. And so the dimension of the half exterior power of vector space is just the amount of subsets of size R of a basis of the vector space. So it's this binomial coefficient. And so if the space is fine dimensional, you can use the binomial theorem and note that the power of the dimension of the whole exterior algebra is 2 to the dimension of the vector space. Just kind of dimensional considerations. Now, we can try to go back to visualizing things, and things work out quite nicely. Many of the unpleasant things that we had about the tensor product in visualizing it go away here. In fact, this is one of the main reasons why exterior algebras are so useful and why we care about them here. They are geometrically relevant because you can think about them in this way. So, oh, actually, sorry. I think I'll get to that in a moment. That'll be the next slide. But before that, this will be a slide in 2 slides. Before that, we want to, or it's useful to also think about how this relates to multilinear maps. Because just the same way how we can characterize the tensor product by multilinear maps, you can characterize the exterior powers by alternating multilinear maps. And what that means is that there are multilinear maps which map R tuples of vectors to 0 whenever 2 agree. Or, well, here I've written it as whenever one agrees with the next, but actually one can check that it's equivalent to whenever 2 agree. Makes a nice exercise. And also if the characteristic of k is not 2, which means precisely that 1 plus 1 is not 0, which if you've not done much algebra might seem absurd, but if you think about such things as finite fields, so kind of number systems, we have finitely many numbers, there are only so many sums. If you keep adding 1 to itself, you're eventually going to get 0. And so whenever that happens immediately, that's called characteristic 2. And whenever you don't have characteristic 2, you can also characterize this by the fact that switching 2 of the vectors in our n tuple or r tuple we input into the multilinear map results in a change of sign of the result. And then for a general permutation, which is this notation sigma and SR, SR the symmetry group of R letters, all the permutations, so possible reorderings, bijections from the set of 1 to R, 1 through R to itself. We can, for any such projection, count the number of times it switches to elements, and that number is not invariant, but its parity is invariant of the permutation. And then if the parity is even, we call the permutation even and set its sign, which had noted its absolute value sigma to 1, and otherwise we call it odd and set the sign to -1. And so you can check that if your characteristic not to be alternating, it's equivalent to exactly have this sign switching whenever you switch the vectors. Each time you switch to, the sign switches 1 time. So in general, for permutation, switches as many times as the sign changes, so the signature of the permutation. And so, yes, also note that very importantly, we do not have an alternating product of vector spaces. We only have powers, or exterior product, exterior powers. Because for this notion of alternating maps, we crucially have to suppose that elements are the same in our tuple. The vectors we put together are the same. So the vector spaces we started with are the same. I mean, also if you think about the exterior algebra, we require that V wedge V is the same. I mean, we started with the tensor algebra for vector space of one vector space. Of course, if you want multiple vector spaces, you can just take them together, take the direct sum, and then take the algebra construction. But a priori, you always have to work in some one ambient space. Okay, well now we can get to now we get to the universal property we get, which is just completely analogous to that of tensile products, except now instead of talking about multilinear maps, we talk about alternating multilinear maps, and we get that the RF exterior power of a vector space is the initial alternating multilinear map out of its RF power as a vector space, just the direct power. And so we have this factoring. It's the same thing, and this is exactly characterized here. So this is just the same thing as the tensor products, but now with exterior powers, and we have to suppose all the vector spaces be the same, so we take these powers. And so if we have a multilinear alternating map out of the RF power of a vector space into some other vector space, then there exists a unique lift of it to a linear map, such that the composition out of some V to which we have a multilinear alternating map out of V to the R. Oh, sorry. That's of course not good notation. The V below and the V above are different spaces. But well, so it's not okay. This is a typo. It should be V to the R to some V prime, or V. So the V here in the codomain of M refers to the thing that we put the exterior algebra into. But okay, essentially, all I'm saying here is that we have the same universal property we get for tensor products, except we, of course, now have to require all the vector space to be the same with the product, and we take multilinear alternating maps. Okay, maybe this is a bit not put too cleanly, but it's the same intuition as the tensor product, just now we do alternating things. Also, if you do over algebra constructions, you get very similar things. You get symmetric powers, and then you get symmetric maps, so you can do Clifford algebras, and then you get something with maps which have certain property with some products. You can always get these universal properties, because again, the tensor algebra has its universal properties. You can always induce universal properties from that when you take quotients. Okay, but now we get to what I teased way back 3 slides ago. It's the nice geometric properties we have. We can visualize quite nicely. So many things are fixed. Now, if we are in dimension D, we no longer have d factorial ways of labeling our vectors. We have only 2. Essentially, what we've done, we've said that we can rotate by 90 degrees, and we've killed orthogonal differences. So, of course, orthogonality here comes just because I'm drawing it this way. In general, it will be just regarding the basis you draw translations. So, for example, let's consider in the second exterior power of R2, E1 wedge E2. Well, as mentioned, this is negative E2 wedge E1. So if we want to switch the numbering of the vectors via wedge producting in our blade, we just can put a negative sign. Alternatively, we can also rotate in the sense that we just switch, well, a negative sign, we can take it into one of the vectors, and then we flip it over, and then this turns out to be exactly the rotation we want. And this way, we get a notion of what's called orientation, which is exactly this sign we have, depending if we're working with E1, depending, yes, if you're working with E1 wedge E2 or E2 wedge 1. Yes. So another thing that this fixes is that these degenerate kind of tensors we had, E1 tensor E1, that draws as a vector with multiplicity 2, are now just 0. So it's really quite purely geometric. And this also explains how the dimension falls down so much. We no longer have all of these multiplicity things to worry about. We just have like the geometric objects, the sort of parallelograms, the high-dimensional generalizations. Okay, so one thing to note is that both with the tensor algebra and then as its quotient, the exterior algebra, we have this notion of kind of order or rank or degree. Again, there's very different conventions on what to call it, of elements, kind of the amount of vectors you put together. And this is a notion of a grading, and it's very general. So I'll give a very general definition here, though you can usually do this just with the naturals or the integers, the reals. So in general, you have some set I and some commutative binary operation that is also associative. These conditions ensure that you can do nice things, such as taking tensor products of your um, graded things. So we have this set. So in general, you can just think of the natural numbers in the addition. This is the most relevant condition, most relevant situation we'll have in the book. We'll also look at the cyclic group for the two. But the reason I want to put this definition in generality here, because I think it's helpful to see that there's a really general construction you can do in many situations. In fact, sometimes you don't even need commutativity, it's just useful for many things you want. So let's take this indexing set, let's say naturals, or well, just some I. Then a grading on some algebra is a direct sum decomposition into a family of linear subspaces indexed by your set, such that whenever you take an element out of the ith and the jth and take the product, it lies in the I plot jth of these linear subspaces. And this is where we need this binary operation. So for example, if you look at polynomials, so this is this K algebra where we have all the polynomials in one variable, we can grade it by the degree of polynomial, and then say that we have the elements in our ith subspace, just multiples of x to the I. In general, again, you can do overgradings. You can also do what's called group rings, and you put any, or even monoid rings, put any monoid here instead of the naturals to grade. But if you just do the usual polynomial ring, you get the natural grading. It also kind of nicely illustrates how you have a correspondence between the grading you have on the monoid ring and the monoid you use. So in general, usually when people speak of a grading, they mean a grading with naturals to the integers. You can do this in very greater generality, and as mentioned in the book, we'll also consider grading by the cyclic group of order 2. So to finish off my talk, I will move on to talking about multilinear forms, which is a topic we'll need in differential geometry, and is kind of very, I would say it's the main point of practicality in multilinear algebra. And multilinear forms are just multilinear maps, which map some power of a vector space to the base field of scalars. They can also be, of course, alternating, as multilinear maps can, and multilinear forms we call bilinear forms. The reason this notion is so useful is that you can think of in R form, a multilinear R form, as a map from the half tensor power of our vector space to the base field, as just with the universal property of tensor product, a linear map. And you can think of this map as a sort of assignment of volume to any pure tensor, and combination of those. So you start with some tensor, for example, the tensor AB tensor CD. Now, if you want to define the bilinear form as just a bilinear map, you don't have to do tensor product, you just view them as an ordered pair of vectors. And then we map it somewhere. For example, I can map ABCD to A minus B, C minus D. This kind of is like the area you would have. I mean, not really, this works pretty poorly, but you can intuitively think about this being something like area. You have all of these notions of volume that arise. And so it's very useful in, again, differential geometry if you want to put volumes on linearized places in your spaces, which we'll get later. And it's something that's useful also in pure multilinear algebra, because volumes have quite some power to come with. So that's what a multilinear form is. And so you of course have the usual volume. A multilinear form is something which intuitively abstracts away volume, but you also have the kind of usual notion of volume on RD. And if you look at the corresponding multilinear form there, you get the notion of the determinant. So what you do there, you take some d vectors in RD. You think of the parallelogram, the span, and if you want to know the volume of that, well, by classical linear algebra, this parallelogram is the image of the unit cube under the corresponding linear map from the edge, the outer edge vectors. And so to get the volume, it will be the unit cubes volume 1 scaled by the determinant of the linear map. And so we get this multilinear form. And it is alternating, which means if you switch two of the vectors, you kind of change the orientation and get a minus sign in your volume. And thanks to that, we can actually view this as a map out of the exterior power of a vector space. In general, by the universal property of exterior powers, we know that an alternating R form is the same thing as a linear map out of the R exterior power of a vector space. And so, in particular, we can think of our determinant as a map of the d exterior power of Rd into R. Now, this is the unique linear map, which maps the blade E1 wedge En to 1. And the fact this suffices can be noted from the fact that the dimension of the deep exterior power of Rd is 1. Because as we've noted, well, if you have all the wedge products of basis elements as a basis, except you kill everything unnecessary, you cannot have repeats. And so because we only have d basis elements, again, this should be a d not an n, not a typo, we have that just any non-zero basis, sorry, any basis element will be a wedge product of these E1 through En in some order. But as I've seen, all of the orders don't matter. We can just switch them for a bunch of different positions to get minus sign. And so we really have only one basis element. As you've seen, this is just d choose d, the dimension 1. And so it suffices to define our determinant map on any one d blade. It will be a basis, as long as it's not 0, of course. It will be a basis for our exterior power, and so this will uniquely define a alternating d form on Rd. In general, there exists, up to scaling, only one alternating d form on Rd. And so, in a sense, this explains why it's called a form. We just specify one choice of basis, one d blade, and we say that this maps to 1. And then anything else can be reduced to the situation and obtain the volume of this way. So, for example, if we want to map 1, 1, wedge 0, 1, you can visualize it as this kind of blade which goes diagonally and then upwards as our parallelogram. If we want to map this to 1, well, we can actually notice it's the same thing as just E1 wedge E2, because this sort of non-orthogonality can be killed off using the exterior product, and we get back our usual determinant. And in general, whatever you put here, you will just see that the corresponding alternating linear form we get will be off by exactly the factor of the determinant of this d-blade. So this is a special case of what's known as Hodge duality, and this is not something we directly use because I will not elaborate on this here, not to stretch out the talk too much. But in general, you can note that the dimension of the Rth exterior power of a vector space and of the complementary dimensional exterior power of a vector space, where complementary means the dimension of the vector space minus Rth power, exterior power, they're the same, because if we choose R things out of some D, it's the same thing as using D minus R out of some D elements, just by complementation. And so in general, we have this nice way of putting them into correspondence. This is what the Hodge saw does. But I'll not go into this. This is just a special case of it. And okay, one last thing I would like to talk about is bilinear forms and how they correspond to angles somewhat. And for that, first note that any R form on any fine dimensional vector space can be decomposed into products. So earlier at the very start of the talk, I alluded to how tensor products really are kind of fundamentally about multiplication, and this is sort of what I meant. Any multilinear map out of KD to the power of D to the power of R to K can be written as a sum of products of the coordinates of the components of my input vector. And in particular, in the case of R equals 2, a bilinear form, we just get a matrix of coefficients we have to worry about. And so bilinear forms are in fact in bijective correspondence with matrices, and this is very convenient because now we can think of properties of matrices as properties of bilinear forms. We just note that any bilinear form necessarily maps some, let's say, in the case of d equals 2, some a prime b prime to some factor a times a prime plus some factor a times b prime plus some factor b times a prime plus some factor b times b prime. And so we get this matrix of these factors, this 2 by 2 matrix. In general, the d by d matrix of these the dimension. And in fact, we can put properties of bilinear form in correspondence with properties of the matrix. So the bilinear form will be alternating precisely when the matrix is antisymmetric. You can just kind of go into the correspondence definition and note that this is how this reads out. It will be symmetric, which means that it maps xy to yx, to same places where it maps yx, precisely when the matrix is symmetric. It will be what's called non-degenerate, precisely when the matrix is invertible, and it reads out as the condition in terms of the bilinear form that any non-zero vector will necessarily have a non-zero vector whose value the bilinear form is non-zero with. Alternatively, if you put the converse as this. And another useful condition to know is that of positive definiteness of real bilinear forms. So this is the case when the ground field is the reals. And that's just that this determinant of the corresponding matrix is positive. This means that the valid bilinear form on any non-zero vector with itself is positive. So if one takes these three last conditions, symmetric and general positive definite, and requires all of them, in fact, the third one follows from the fourth, so that any positive definite linear form is non-degenerate, because of course, if the determinant is non-zero, sorry, if the determinant is positive, then it's non-zero, and so the matrix is invertible. So if you consider these conditions and impose them on some bilinear form, it's called an inner product. I mean, there are varying conventions of what inner products are, but in classical functional analysis, this is the definition of an inner product. And these conditions can very nicely allow us to talk about angles, because if you think about it, if you define volumes of two plates, well, this is not longer two plates because we have symmetric bilinear form, but if you define kind of volumes of parallelograms, and yes, it being symmetric means that it doesn't matter which order you put the vectors in, then by knowing the kind of, or I guess in two dimensions would be areas, by knowing the area of this parallelogram, you kind of estimate the angle. And this way you can correspond this map, which takes a pair of vectors and gives you a number as kind of the area of the parallelogram to the angle between them. And this is something quite useful in, say, Riemannian geometry, which we'll also get to. So I'm not elaborating on this too much. I will talk about this in greater detail later and talk about specifically Riemannian geometry. But that's just something very useful to know also. In our context, this is one way you can extract angles from the whole multilinearly algebraic discussion. Okay, so that would be the end of my talk. I've just put some minimal further reading references here. You can take a look at, this is a geometric measure theory book, but actually it has a very excellent first chapter on multilinear algebra. It covers a lot of things in detail, also elaborates on, say, Hodge duality and such things. Or for more, so this would also go kind of more into detail on things I've not talked about. Or if you just want a more elementary uh, repetition of the things I've talked about, you can take a look at Grubb's book, Multilinear Algebra, where he talks at very great length and detail. Well, it's not long, but he very explicitly and in a detailed fashion talks about all of these concepts, elaborating on how they work together. So you can kind of take a look at these books. I mean, there are many books on the subject. It's a very useful thing. Again, in all of differential geometry, this is kind of the approach people have been taking to kind of do linear algebra on all of the linearized things, all of the tangent spaces. I mean, I don't want to use the word because I'm not defining it yet. I'll comment back next week. Okay, so yeah, that's the end of my talk. Next week I'll talk about elementary differential geometry things. I'll post the outline of the talk in announcements, or just kind of the topics I'll talk about. Then the week after I'll talk about Riemannian geometry and then Lie theory. So yes, thank you everyone for attending. Seems we had quite a good amount of people come. Yeah, I'm sorry about the many typos in the talk. I'll try to fix the slides later. And I'll upload the recording on my YouTube channel. So I guess before we end the recording, any questions?
All right, I did have a question on, would we even run into any non-associative algebras in spin geometry?
Okay, so one person asked if we run into non-associative algebras in spin geometry. And I do think the Octonians have a useful. I mean, if you think about spot periodicity, it's periodicity of 8. And well, I'm not an expert on spin geometry, but I'm pretty sure that can be put into correspondence with the octonions. Oh, yes, of course, the algebras, which instead of associativity satisfy an altered version of it, the Abel-Jacobi identity. Thank you.
I tried looking up octonions in the PDF, but it's not searchable. RIP.
Well, I mean, even if they doesn't explicitly put it this way, that I'm
Yeah.
pretty sure that it relates to that. But yeah, the algebras are a much simpler example of non-associative algebras you care about. And I mean, okay, I mean, calling them non-associative is a bit cheeky because you kind of just replace associativity with the Abel-Jacobi identity, but it's still non-associativity. Okay.
Got it. Okay, thanks.
Any other questions? Well, I guess if not, then I'll stop the recording.